I work for OERD, the Office of Energy Research and Development at NRCan, and this has nothing to do with that. I am talking, these are my own opinions, it's a personal project, so let's get that out of the way. So I'm going to talk a bit about modern hydronic systems and try to frame this around a couple of questions. I personally have noticed an awful lot of interest in residential hydronic systems in the last few years, as many of you may have as well. So I'll talk a bit about why that is, some of my theories as to why that is, and then how can we apply some of these modern hydronic techniques to address common building wish list items. So you could define modern hydronics in an awful lot of different ways, and this is by far an exhaustive list, but a couple of key points that I think about are low temperature heating. You know, historically, boiler-fed systems have operated at really high water or steam temperatures, 180 degrees Fahrenheit or more, and they are really hard to retrofit. There are some high temperature heat pumps that are coming to market to address that market, but on day one with a really good building enclosure, there's no reason that we should be designing hydronic systems to operate at any more than 120 degrees Fahrenheit on the coldest day of the year. And we can go colder than that actually. And then the next one is a bit redundant. Heat pumps are reversible by nature, but the idea here is that as we move away from boiler systems, which really only do one thing, make hot water, and using heat pumps in our hydronic systems, we now have the ability to produce chilled water, and we can use that to cool the building too. So historically, when you've had, say, a custom home with in-floor heating fed by a boiler, you'd have to provide a secondary system to do the cooling. And now we have the flexibility to do that with chilled water, all with one system. Modern heat emitters can look a bit different. We can also use the ones we've used for decades, but these are a few examples of radiant ceiling panels that we considered for this project. We didn't end up actually using them. We didn't go with radiant cooling, but you can do radiant heating and cooling. You can use low mass radiators, which are a great fit for passive buildings with high solar heat gain if we want a system that can respond really quickly when the sun comes out, where high mass systems aren't your friend. Chilled beams are more of a commercial technology, so I won't focus on that today. But fan coils and fan-assisted radiators are also really interesting. So these are not radiant systems. Like the fan-assisted radiators can act as a rad, but they have a little DC fan to get convective heat transfer as well, which starts to get interesting when we can play with the sizing of those. You can get them with drain pans, so you can use them for cooling now. And then fan coils is where I'm going to focus today, which is basically just a forced air system, but we're using water instead of refrigerant as the heat transfer medium. Yeah, perfect. So there was a really, really great two-part series on this on the Building Science podcast in December and January. I recommend if you don't get enough hydronics from this today, go back and do a 2-hour listen to that. But they really nailed it. They captured my feelings around this, which is one of the biggest things we can get with this is decoupling. So if you've got an air-to-air heat pump system, a split system that uses refrigerant as a transfer mechanism between indoors and outdoors, when you need heating inside that home, you need to run the compressor to meet that load in real time. There are some systems now that have battery backup that are being tested in the Northeast states, from what I understand. So they can do a bit of load shifting, but we can do a lot more of it with hydronics. So the idea of decoupling is decoupling when you need to consume heating and cooling in the house from when you want to generate it. And you can do that with buffer tanks. Buffer tanks can only do so much, but I think where it gets really exciting is as technology evolves and we start to incorporate phase change materials that have a much, much higher density, then we can start to shift for longer periods of time. So then we can produce when there's excess renewable capacity on the grid, or when we're about to see a price spike, we can store energy and coast through those periods, or the time of day when everybody gets home and turns on their oven and everything. And then we can optimize heat pump sizing. We're seeing this on a very large scale right now, so stepping away from residential for a moment, like big towers in New York City that have, they've been heated with fossil fuel boilers. As they decarbonize, if they're not going to go geothermal, then they're probably going to go air to water, and their most precious resource is the roof space on which to locate those air to water heat pumps. And they're very expensive, and they're very heavy, and they have structural considerations. So if they can do storage, which is usually phase change in the form of ice storage in the basement, then the engineers are already doing this problem solving of optimizing, can I buy less peak capacity and buy more storage and coast through those times? So we're kind of at this inflection point where peak capacity used to be really cheap because you could buy more boiler capacity for not that much money, and storage was complicated and expensive. And as we decarbonize, we're flipping that, and now peak capacity is becoming relatively expensive and storage is becoming relatively cheap. Next slide. And then flexibility, obviously, when it comes to, first of all, the density of water and the specific heat of water make it a big advantage to move a lot of heat in a lot less space compared to air. This is an IR image of a couple of 1.25 inch pipes in my house that's transferring all of the low temperature water from the basement up to the first and second floor, and it takes virtually no space at all. Endless options for heat emitters, I mentioned that already. And I would argue that zoning is less complex with water side systems than it is with air side systems. So then the future proofing aspect, we were in the midst of refrigerant transition. You're all probably aware after the Kigali agreement, or the amendment I should say. We are phasing down the R410A that has dominated all of our refrigerant systems in homes for the last 20 years or so, because it has very high global warming potential. We've reached this point of like these stepping stone technologies, stepping stone refrigerants that have lower GWP but higher flammability. And our long game is to get to natural refrigerants like CO2 or R290 propane, which are already kind of dominating the market in Europe. Most of the air-to-water heat pumps sold over there are R290. But if we set up the system to have hydronic distribution and all the refrigerants in the yard, then we don't really care. Like we can, when the heat pump that we buy is at end of life, we can swap it out without having to do a major overhaul because we're not bringing any refrigerant lines into the house. The thermal storage market is evolving, so I'm not doing any of that on day one really, but we could add it in the future, which speaks to the modularity of these systems, that they can be repiped and modified as time goes on. And I think the controls market's constantly evolving. We'll see more that's suitable for chilled water cooling in homes, and I think we're really gonna see more controls that automate that load shifting component that we're talking about. So the drawbacks, I mean, I showed you this exact picture 2 slides ago because some of you probably looked at it and were like, yeah, that's expensive, and you'd be right. So it is complex and expensive because there's a lot of bespoke design that goes into this and a lot more labor compared to putting in an air-to-air heat pump, which needs some ductwork and one thermostat wire, and it's pretty simple. They have really great onboard controls. There are a lot of different directions you could go with this, and you need some specialized trades, at least somebody who knows how to install these systems. And the biggest thing is you need somebody who's willing to maintain it for the life of the system and understands it. I know Mike's going to talk about unintended consequences of high performance systems, and that's certainly one risk. And as far as performance standards go, there aren't any in North America for air-to-water heat pumps currently, but there is a CSA standard and an AHRI standard coming, so we'll be able to compare apples to apples for these systems very soon. Okay. So now on the common request, the flexibility of these systems, how can we use that to address common building desires? So I've listed a few of the ones I've heard over my career. Minimal architectural impact. Often people really don't want to see the mechanical system, especially they don't want bulkheads. We can get away with fewer or no bulkheads with some of these systems. Open floor plans have obviously dominated the last 20 years of our construction industry, our single family home industry. That makes it very hard to get a large duct from the mechanical room, air source heat pump up to the far-flung second floor. We can solve some of that by using piping. Fashion over function, certainly in custom home design, we see people making choices based on what looks good and maybe not the grills the engineers would have selected. Now that isn't something that's inherently solved by hydronics, but we do have a lot more options that we can work with. And a lot of people have said to me over the years that they want to be able to keep their bedrooms cooler, which is, again, you can do it with air source systems, but I find it's easier with hydronics, and everybody wants a quiet system. So now we finally get to the case study. This is a home we built last year. Terrell was our architect, and Evolve built the building. They did a fantastic job. The numbers, we did all the stuff you're not supposed to do. We did a guillotine wood-burning fireplace with a chain-actuated flue damper. We have a direct air combustion duct going into that firebox with a damper. We have a direct vent range hood. I will die on that hill. It has a motorized damper on it, and it has a makeup area in it with a damper on it. And we hit 0.58 ACH 50. The heating loads are 6.2 BTUs per hour per square foot and 7.2 in cooling, which I was pretty happy with. It's a 100% electric building, except for the wood-burning stove. Here's a simplified hydronic diagram for the building. So again, this is a monoblock air-to-water heat pump, which means it's built in a factory. It has a self-contained refrigerant system. When it arrives on site, what we do is connect a control wire to tell it what to do, power wire to tell it to send power to it, and then there are 2 pipes, a supply and a return. No refrigerant goes past that point into the building. So we run a glycol water mixture outside to that unit. It only does one job. It makes hot or it makes cold, and it sends that water back in. So in heating season, we're making hot water and sending it to that buffer tank on the bottom. And then it's trying to maintain a temperature. And then from there, The pumps on the other side of the diagram are pulling heat out of that tank and sending it to the in-floor heating in the basement and up to the fan coils on floors 1 and 2. That buffer tank also has a copper helical coil in it, and so that it's full of glycol water mixture that's kept hot all the time. And then the domestic water, when someone takes a shower, it goes through that coil and it gets preheated and then put into a final electric tank. So this one outdoor unit is doing all of the home heating, most of the domestic water heating, and all the home cooling as well. So in summertime, it flips, it makes chilled water, and P3 sends it into the chilled water buffer tank. They have their own problems. That's not the point of today's talk, though. And then it goes out to the fan coils from there to send chilled water throughout the house. And then when we're dealing with chilled water, we need to be really careful compared to dealing with hot water in houses. So this is closed cell elastomeric foam insulation. You can see, if you look closely, the shininess. All of those longitudinal seams have been glued. It's vapor tight. You can see the nice job on mitering the corners too, and gluing that, also vapor tight. And then the contractor wrapped all of those exposure points with tape just to protect them. Cortez Enterprises was the contractor. They did a fantastic job. So now, as far as the architectural impact goes, the house was built with 9-foot ceilings. So here you see the ground floor plan. Anything that's shaded is been dropped deliberately to 8 feet to accommodate the system. So it is a fan coil system. We're delivering water, either hot or chilled water, to these fan coils, and then it transfers to air and runs out to the spaces. So the one at the top of the screen is in the pantry. We have a removable ceiling in there to be able to access and maintain that unit over its life. Below that, you see a red bar. That's an 8.5-inch chase that goes from the mechanical room in the basement all the way up to the top of the house. And that way we can run ventilation ductwork and a central dehumidifier ductwork that circulates through the home. And the hydronic piping comes through there and then branches out to the fan coils. We have a second one here, again with a removable ceiling. We kept the ceiling low at 8 feet through the bedroom, and there is one bulkhead. Everything else has been coordinated and runs through the TJIs. So no impact to the ceiling. Here we have the second floor, same story, 9-foot ceilings, 2 fan coils, one for the north zone, one for the south zone, and dropped the whole hallway ceiling and part of the bathrooms, laundry room, and one bulkhead in that bedroom. Everything else is 9 feet, so we didn't touch the ceiling heights. So this is what the system itself looks like. This is from a company in Italy called Giacomini. Eden Energy in town here supplied me with these. What makes these interesting is that most fan coils just have a coil and a single fan in them, and if you wanted to subdivide that air, you could put in a motorized damper system, but that adds additional complexity on site. What's interesting is inside this box, there is a single coil, but there are 4 fans. So that duct gets piped out to a bedroom, say, and there's a thermostat in that bedroom, and that thermostat tells that fan to run or to stop if the point's satisfied. So in our instance, we've got one upstairs that has 3 ducts. One of them goes to my daughter's bedroom. She likes to keep her room at 18 in the winter. She can do that. The same fan coil, my other daughter likes to keep her room at 22 in the winter, and she can do that, all from a single fan coil. You could do this by putting a fan coil in every single room, and lots of people have, but it's kind of like, where do you want to do maintenance and how much maintenance do you want to do? Because then you're introducing a drain pan in all those rooms and a filter to change in all those rooms. And if you go to a single air handler in the basement, you lose a lot of that zoning capability, but you've got the lowest maintenance. So this is kind of a hybrid in between where we've got 4 points of maintenance through the house, 4 fan coils, and I can live with that because of the level of control that we're getting out of it. So, nobody had used these before in Ontario. So we plotted them full size, and then we used those for the rough-ins so that we made sure that all the ducts and pipes lined up where they should. And then luckily, when they showed up on site, there weren't any surprises. This is the 4-duct again with the flex collars installed now. They're 6-inch, we step up to 7-inch after the flex collar to try to lower the velocity moving out through the house and keep the duct velocity low. This is before the hydronic connections had been done or the control wiring. So that is the second floor ceiling where we've got those 2 fan coils hidden. You absolutely need to think ahead to how you're going to service these units. You can't bury them. So that ceiling is all removable for maintenance over the life of the system. But also, had we just done a drywall ceiling, we would have had access panel, filter, access panel. Instead, we did this. There's an acoustic backing on that product, and then we removed it in areas where we wanted to provide an active transfer through to the return grill. So I have taken it down to do it. It's a pain in the ass. I'm gonna have to come up with a better way of getting to just the filter without taking down the whole thing. So there'll be a modification to this in the future, but that was kind of, yeah, we looked at a lot of products, and this is the best we could come up with at the time. So this is laying down on the floor in the mudroom on the left side and the foyer on the right side, looking at that four-duct in its final arrangement. So there's a removable ceiling on the right side to be able to access that unit for maintenance, which should be infrequent, I hope. But on the left side, we need to access that all the time. So there's a pocket door in between that's louvered to provide an airflow pathway back to the return grill so we don't choke it. That is a standard 24 by 24 inch by 2 inch filter frame return, which is my favorite detail for return grills, because now rather than like the long, skinny, weird filters that come with these units and all kind of fan coils that look like that, we just threw those in the garbage. Never have to try to find them, because that can be challenging. But now for the life of the building, you're ordering stock 24 by 24 by 2 inch pleated MERV 13 filters, which are really easy to come by. They're interchangeable. And when you oversize them like that, you slow down the air and the pressure drop is pretty much negligible. So yeah, that's it. We have energy monitoring, we have indoor air quality monitoring, we have temperature and humidity monitoring. Everything's been good so far. I don't have enough energy data to make it worthwhile to present it today because we've only gone through our first heating season, but please feel free to reach out to me and I'd be happy to share it in the future. So.